All right. So when we had last clicked off, we had gotten through that ds is going to be negative r cosecant squared d theta. And so what's going to happen here then is that we're going to bring that up. And instead of ds, we're going to end up putting all of this in for it. And when we do, a whole lot of stuff cancels because cosecant is 1 over sine. So everything cancels out. At least a lot of things do. We can scoot some stuff out to the left of the integral sign. And then we're left with basically the integral of sine theta d theta from pi to 0. And if you're wondering why it runs from pi to 0, we're just trying to take this thing, and by thing I mean the little current length piece, to extremes. So if it goes way, way, way to the right, like way, 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 way off the computer and everywhere else, way out to the right-hand side, this thing is going to go essentially to pi. It's going to be pointing to the left. And if we run our current length all the way over here, right? So then we'd have to have we'd have to have our vector, there we go, come with us this way. That would eventually become flat if it went farther and farther this way, which would be where the 0 comes from. So that's why we have those bounds the way we do. Come on, buddy. All right, well, there we go. Oh, man. All right, well, anyway, that's why the bounds are the way they are. Boop. There we go. And if you haven't flipped or anything like that, and then you're going to be going from 0 to pi instead, and you just end up with a funny negative in there, which is just, it doesn't really matter. It's only for magnitude that this equation is really important. So plugging in for everything, we get the integral sines cosine. Putting in cosine of 0 is 1, cosine of pi is -1, so minus -1 becomes plus +1. That's where the 2 comes from in the numerator. And when everything cancels out, we get B equals mu naught I over 2 pi r, which is the magnitude of the magnetic field from a current carrying wire via the Biot-Savart law, which is what you should have learned last year when you learned magnetic field from a current carrying wire. Now, there's different versions of that. The first is from an infinite wire, right? This is the kind that we just solved, where we're looking at some point that is immediately over a wire that is super duper long on either side. If we look at something that is set up from a semi-infinite wire, and it might be funny to have something be semi-infinite because you're like, dude, it's either infinite or it's not. That's true, but the point that we're analyzing here happens to be over the end of the wire, not over the middle. So it's infinite, but only infinite in kind of like over here. So as you can imagine, if a fully infinite wire is over 2 pi r, then a semi-infinite wire would be half that, which would make it over 4 pi r. And there are also equations for if you're looking for an arc of wire, and that would be B equals mu naught I phi over 4 pi r, where phi is the length of the arc measured in radians. And just if you're curious, if you want to know what the magnetic field is for a circle of wire, you could use that equation. But just keep in mind that phi then would be 2 pi, and then plugging in, you would get what we have right there. And that's probably a good spot to press pause there.